All right, everybody. In this video, I want to look at the idea of a directional derivative, which tells us the rate of change for a multivariable function when moving in a particular direction in the domain. This may or may not be review, but it is good to brush it off now at the moment in the semester for what's to come. So first, I just want to recall some basic ideas of multivariable functions and visualizing them. So here we have an image of a multivariable function. We're going to be working in two dimensions in this video. So this is a function f of xy. We could have drawn a 3D image of the graph, but instead we're drawing a contour plot in which we can see the different level curves of the function given here. So this is a visual representation of our multivariable function. Now, if this function is f of xy, I want to recall that the gradient vector is or maybe I should say the gradient is an expression that we can compute, and this is a vector-valued expression consisting of the partial derivatives of f. So this is grad f equals, and then the partial x derivative, comma, partial y derivative. This is a vector-valued expression with two functions in it, the partial x derivative and the partial y derivative. But at any given point that we want to plug in, the expression gives us a vector. So that's why I'm calling it a gradient vector. So in the image up above, if I were to plug in a point, let's say the point -2, 0. Is that right? Or this is -3, 0, this point right here. If we were to plug in that point into the gradient, we would get a vector, f sub x at -3, 0, comma, f sub y at -3, 0. And that vector would point in the direction of steepest increase for the function f at that point. So at this point, we can see that the function is increasing most rapidly if we were moving roughly in this direction. And so we can imagine that the gradient, if we explicitly computed it, would point in that direction. This is the direction, I should say the gradient vector is always perpendicular to the level curve. So looking at it, we should see that that would form a right angle there. And it's pointing in the direction of steepest increase. So here you can see this vector is pointing from a height of 1, we're on the level curve c equals 1, to a pointing up, so in the direction of the level curve c equals 2. So our gradient vector will always satisfy these properties. However, if we wanted to look in a direction other than the gradient direction, so in this case, the gradient direction seems to be maybe southwest or west-southwest. But if we wanted to look in a different direction, how could we calculate the rate of change of the function? How quickly our function f was increasing or decreasing? And so let's give this a go. Let's take a look at this. So to calculate that, first I have to maybe create a good framework for understanding the rate of change of a function in a given direction. And we should be looking at a specific point as well. So let's specify a point. I'm going to call it point P, and we can call that point maybe P1, comma P2. This is the point that we're looking at, and we'll just go ahead and keep it at this point -3, 0 in the picture, but in the computation, I'll keep it general as P1, comma P2. So that is the point in question. And then let's also create a vector, maybe blue, for our vector, and that will be indicating the direction that we want to compute this directional derivative in. So from P, maybe our direction is pointing off at this sort of slanted, skewed angle here. It's not quite perpendicular to the gradient vector. It's not in the exact same direction as the gradient vector. And really, this is just drawn arbitrarily. This could be any vector, but it is going to be a unit vector. So let me call it vector u. And down here, where I'm recording my information, vector u is going to be a unit vector indicating the direction that we care about. So vector u could be the vector u1, u2. Now, to identify what we mean when we talk about a directional derivative, we mean the rate of change of this function as we move in the direction of vector u, starting at the point of vector p. And so to formalize this, we can create a line going through vector p in the direction of vector u. And I'm realizing now that this was probably the wrong color to use. That's the same color roughly as our gradient vector. Let's use orange. So the orange line is going to be this line moving through P in the direction of U. And let me give this a name. Let me call this L of T. And so we already know how to parameterize L of T as a parameterized curve. We could say L of T is equal to, and this was our formula for parameterizing curves. If it goes through the point P, we're going to vectorize the point P by creating the vector from the origin to P plus T times the direction we're moving in. So this is vector U plus T U. And we can simplify this. This is P1, P2 plus T U1, U2. And so that's nothing more than the vector valued expression P1 plus T U1, comma, P2 plus T U2. Okay, and so at any given time t, that expression points to a point on this line. At time 0, it's pointing at the anchor point P, and then it moves in the direction of U at speed 1. All right, great. So with this framework, the rate of change of the function f in the direction of u is going to be equal to the derivative. So rate of change, we're talking about a derivative here, but it's going to be the derivative of the composition function f of L. And so let's explicitly write this down. So the directional derivative, the derivative of f in the direction of u is the derivative of f of L. And now notice f was a function of two variables, x comma y. L is a vector valued expression that just has t as an input, but has an x of t and a y of t as outputs. So the expression f of L is just a function of t. So f of L, we're taking its derivative with respect to t. And we can do this either by creating the composition and then taking the derivative, or by using our knowledge, newfound knowledge of the chain rule. And so the derivative of f of L with respect to t, by our knowledge of the chain rule, is going to be the gradient of f dotted with L prime of t. And so we've identified this once we can calculate the derivative of L. Now, going back to our definition, remember P1, P2, U1, and U2 are all constants. The variable here is t. And so this becomes the gradient of f dotted with the vector. And now the derivative will be 0 plus 1 times U1, comma, 0 plus 1 times U2. And that is just our original direction vector u. So when the dust settles, the directional derivative of our function with respect to the direction u is the gradient of f dotted with this vector u. Now, I should have put this earlier, but I'll conclude by saying that we have some notation for the directional derivative. The directional derivative is, we write it, we have our direction, so we have a big capital D, indicating that it's a directional derivative. It is of the function f, and it is in the direction, so this becomes a little subscript here, in the direction u, and specify that we're calculating it at the point P. So this is our directional derivative notation, and it's computed exactly as we saw down here, the gradient of f dotted with that direction u, and all of this evaluated at the point P. Okay, that's going to do it for this video. Thank you so much for watching. See you all next time.